Hello, everybody. Section 2.4, acceleration, accelerated motion. Talking about changing velocities here. Not constant motion, but changing motion. So generally we say that acceleration happens when anything is speeding up, slowing down, or changing direction. So the only changing direction that we'll deal with right now is 180 degree change in direction. So if something is moving up and then it starts moving back down, or vice versa, moving down and then it starts moving back up. Eventually, later on, we will talk about turning objects and things that are curving and things like that. But right now, it's all one-dimensional motion, moving in one direction or the other, sometimes both a little bit later. All right. So the ratio of change in velocity to change in time is what we call acceleration. That's one definition of it. Another one is the slope of a velocity versus time graph, which is the same thing, a change in velocity over change in time. This equation right here, delta V over delta T, this little subscript x really just deals with the fact that for the most part right now we're dealing with horizontal motion, but these variables could be in either direction. They could be up, they could be down, left, right, forwards, backwards. We can think of them in three-dimensional terms, but it will only be one dimension at a time. Okay, SI units of velocity, meters per second. So we have these two cars down here, the Corvette and of course, the well-known Chevy Sonic, which we've all heard of. It's apparently really slow. Maybe that's why we haven't heard of it. I don't know. But the Corvette can get to 60 miles per hour in 3.6 seconds, whereas the Chevy Sonic can get to 60 miles per hour in a whopping 9 seconds. All right, so this is just to show how we calculate acceleration and what the units are. So the change in velocity would be from 0 to 60. We convert that to meters per second, and it is 27. So we have 27, our change in velocity, meters per second, divided by the time in seconds. And we get a 7.5 meters per second every second. So we could say that's how fast the Corvette speeds up every second. So that is what we call the acceleration, that change in velocity per unit of time, which is usually seconds. All right. It's normal to write this. I think it makes more sense, I'll say, if you think of it in terms of this, that change in velocity per second. But you can combine these units into a meters per second squared. And once you become more comfortable with this change in velocity per second, the meters per second squared will start to make a little more sense, and you can certainly use them interchangeably. Either one works. The other thing to think about is you don't need, we often change the units to be as consistent as possible so that everything is in seconds or everything is in meters. But one thing that is true is acceleration. If you take 60 divided by 3.6, your units would be miles per hour per second. We're much more used to thinking about speeds, especially of cars, in miles per hour. So knowing how many miles per hour it's changing every second might make a little more sense. But for the most part, we will use meters and seconds. All right, so we can put this data in a graph. We can see that each second, the increase in the velocity of the Sonic and the Corvette, we can put that on a graph. So we have the Corvette with a steeper slope. Remember, the slope is the acceleration. So a higher acceleration than the Sonic. And remember also that the distance that an object travels, or I should say the displacement, is equal to the area underneath the curve. So if this Sonic, if we went straight down to 4 and took the area of this triangle, we would get a number. If we took the area of the Corvette's triangle, we would get a much bigger number, which of course makes sense because in 4 seconds the Corvette will end up at a much higher speed and will cover much more ground. We can find the acceleration from a velocity graph. So we know that as well. The slope of a velocity graph is equal to the acceleration. You won't always have an object traveling at the same acceleration. It may be changing, and that's what we're looking at here. However, we won't ever see a curved line on a velocity graph, meaning that the rate of change of velocity was in constant change. We will see constant constant acceleration, and then right away a different section of constant acceleration, and then a different section of constant acceleration. So we will never see curved velocity graphs. We will see curved position graphs. And if we drew the position graph of this motion, it would be a curved line. It would be an increasing slope. Acceleration graph, from this we take the slope, positive slope, constant, slope of 0, horizontal line, and then a constant negative slope. And that's what this looks like, this acceleration graph. All right, we use these vector diagrams to help us kind of visualize some things. So we have our number line here on the bottom showing position, and our velocity vectors showing how fast and in what direction. So we see this object starts over here, positive displacement or positive position, and it's moving fast. And then it slows down, and then it slows down, slows down, slows down. These orange arrows show the direction of the acceleration vectors. They are pointed in the opposite direction because, of course, the object is moving to the left, but it's slowing down, so its acceleration is pointed to the right. All right. So if we're asked here about the position and the velocity, well, the position is on the right side of 0. That's positive position the whole time. It's slowing down, which is fine, but it's pointed to the left, so it's negative velocity, positive position. So that would be B. If we have a ball rolling, it's moving at some non-zero velocity when it gets to the ramp. So what happens to the velocity as it's going down the ramp? Think about that for a second. Of course, the answer is it's going to speed up, right? We know this. And so what would this graph of velocity look like? So we can draw this and have, let me see, where are we? Here we go. So if we have a velocity graph, velocity versus time, this ball starts with some positive velocity. We're going to say to the right is positive. I don't believe it says it here. No, but we'll say to the right is positive. So say it has some positive velocity to start with. It's not 0. So it starts up here, and it's going to increase as it goes down the ramp. Draw that again. There we go. Something like that. All right. So it'd have some positive slope. So if we now draw the corresponding acceleration graph, well, it's over the same time interval. What is this going to look like? Well, we have, put my little arrows up there. We take the slope of this graph, which is a constant positive slope, and we would have that value up there somewhere. All right. Again, no curves on velocities and no angles in acceleration graphs. They're always going to be flat. The sign of the acceleration, we really want to make sure we have an understanding of this. So an object can move right or left or up or down, and it can either be speeding up or slowing down while doing any of those directions. So we have to make sure we understand what the sign of the acceleration is. Now with these diagrams, with these vector diagrams, when the acceleration arrows are already drawn, it's really easy to determine because right is the positive direction. So both of these are showing acceleration to the right. So you could say, oh, that's positive acceleration. That's really easy. Another way to do it, and now this is when it's given, so you could draw this, but make sure you have a comfortable way to do this, one that you're good at and it makes sense. Another way you can say is, what is the object doing? Well, it's moving in the positive direction, to the right. All right, so that's important. So we can say it's moving in the positive direction. So its velocity is positive. And then what is it doing? Is it speeding up or is it slowing down? If it's speeding up, then we consider that a positive motion for this purpose anyway. If it's slowing down, we consider it a negative motion. But because we have a positive velocity, it's moving in the positive direction, and it's speeding up. And so we're not actually multiplying these together, but if you were multiplying two positive numbers together, you get a positive value. So we can say two positives, the positive acceleration. Over here, now the object is moving in the other direction. So this is a little strange, but moving in the negative direction, and it's not speeding up now, it's slowing down. So we say that's negative. And again, if we were going to look at this as if it was multiplying, negative times a negative is a positive. So we have positive acceleration. All right. Another way, and perhaps the best way and most beneficial for any type of problem, especially an AP type problem, is to sketch a motion graph. So if you know an object is moving to the right, you know it's going to have positive velocity, and it's speeding up, so that velocity is going to be increasing. So you can sketch this graph pretty easily, and it's very clear when you do this that it has a positive slope. All right. And the same thing for here. Now it's moving at a relatively high negative speed to begin with. So you start down here below, and then it's approaching 0 as it slows down. And this also has a positive slope. So the slope of a velocity graph is the acceleration. This is a great way to confirm to yourself what the acceleration is. You can confirm to your teacher. Right? If I'm looking at this and you sketch a velocity graph and use that as your justification to say that the acceleration is positive or negative in the other way, that makes me know that you are really comfortable and you know what you're talking about. Or a grader of an AP test. That's also a very good way to show what you're talking about. All right, just the opposite here. We have an object moving to the right and slowing down. All right. Moving to the right, positive, slowing down, negative. Multiplied together, we have negative acceleration. Moving to the left, negative, speeding up, positive, negative acceleration. And again, the best way, I think, is the graphs. Sketch these relatively quickly, almost as quickly as I just did that up top, and you can clearly see the negative slope. So here we have a motion diagram. It's object moving to the left and slowing down. Acceleration positive or negative? Well, of course, it's positive. The arrows really give it away, but if you use one of the other methods, then it can confirm that for you. I don't like these. I'm going to move on from here. It's too busy. Same. All right, here we go. Mike jumps out of a tree and lands on a trampoline. The trampoline sags 2 feet before launching Mike back into the air. At the very bottom, where the sag is the greatest, what is Mike's acceleration? Is it pointed upwards? Is it pointed downwards? Or is it 0? So this is a good point to pause and really think about this. But I'm going to take some time here and talk about it. And we're going to draw some graphs and think about what we should be focusing on. All right, so I've just drawn this graph here, and this is when thinking about how he falls. When he hits the trampoline, he starts to slow down. He's moving really fast, and he's moving down, which we say is the negative direction. So he starts off with a very high negative velocity. And what the trampoline does is slows him down until at the very bottom, when the trampoline is stretched, he's not moving for a split second. But then the trampoline starts pushing him back up. And so he starts speeding up in the positive direction. So clearly, if you look at this, you can see it has a positive slope. And if we say that up is the positive direction, then the acceleration could only be upward. All right, here are a series of motion graphs. I'm not going to go through all of these, all right? But it's position and velocity. Take some time and go through these. These slides are going to be accompanying this video. You can go through the rest of it. And they're good to practice on. There's maybe 5 or 6 of these. So take a look. If you have any questions about any of these, please let me know. But getting comfortable with motion graphs and the motion of objects is going to be critical going forward.